Let's get started. Last time I talked about the Eisen model. Let's recall a little bit about the conformal blocks and conformal symmetry. Conformal block and crossing symmetry, and also bootstrap. So we know so all primary. Then okay, so so this is a three-point function for all primaries, and then this one depends on the theory. And to determine this C1, 2, 3 is very difficult usually. Rational conformal theory you can do that, but the general conformal theory is not so easy to do that. So there are lots of open problems to determine this C1, 2, 3. Yeah. And moreover, so if you consider some descendant, so the conformal family of phi 1 has lots of descendants. Oh, okay, maybe 3. You can consider conformal family, and it contains whatever, my notation 3 minus n and whatever, and 1 and 2 minus n k and so on. So descendant you can consider. So so it depends on how many times you act on L minus something. And in general, so my notation is like minus k, like this way. Minus, I think k or minus k? Yeah, k. Notation k is k is indeed minus n1 minus nk. Somehow this is a notation, or maybe I should call it NL. So all set of this negative integers, and you can consider phi 1, phi 2, C2, and phi 3, and k, the descendant of C3, and then just consider. Then, so you can have, of course, numerator also change. I think it becomes plus k and so on. And from here, also, this denominator can be determined by Virasoro algebra. On the other hand, the numerator C1, 2, 3, K can be written as follows: C1, 1, 2, 3, and then beta 1, 2, 3, K. And this one can be determined by BPC equation. So recall that so this guy can be written as a product number of L minus N1, L minus N2, L minus NL, and acts on phi 1. This is equal to phi 1 of Z1, phi 2 Z2, phi 3 Z3. Okay. So this is the, and we know the explicit form of the differential operator, so that you can relate this three-point function of the descendant, include descendant, and the primary. So that's what's really happening. Yeah. And we talk about a little bit of four-point function. In four-point functions, you have a whatever Z1, Z2, Z3, and Z4. Oh, sorry, Z4. So it can be by conformal transformation. So you can put 0, 1, infinity, and x. And this is called cross x is cross ratio of Z1, Z2, Z3, Z4. I think in my notation, is in the lecture note is infinity, and then Z2 is 1, and x and 0. Sorry. So this is what I took. In other words, so we take the limit, like my lecture note, my notation 2, 1, 3, 4, and x, and if you can only consider holomorphic part, then Z1 goes to infinity. Excuse me. Okay, so this is what's really happening. So if you define like this way, so one can just write down this one as C 1, 2, 3, 1, 2 P, C 3, 4 P, and then contour block 2, 1, 3, 4 of sum over P, where this, so this is called contour block. And then okay. Oh my goodness, I don't have a time. Please write it down. So times. So yeah, this part is H1. I'm sorry. So it's if you use notation like this. Okay, this is the expression. I can write down, and then here, this quantity can be computed by explicitly. So f, usually this f of 1, what is the notation? 2, 1, 3, 4. 2, 1, 3, 4. P of x is is a function, can be written as follows. So yeah, x hp minus x3 minus x4, and then sum of fk, xk, and this guy can be written our rational function of conformal dimension h1, hi, and the simplicities. So here, so you can consider this guy as you just fuse. So if the schematically, this can be understood as P and 1, 2. My notation is I don't remember. My notation 1, 2, 3, 4. And you just fuse. So you just fuse 1 and 2 and get the this conformal family of 5p. Okay. So in the internal channel, the state that propagated in the middle, and you can just sum over p, sum over all p, all possible p. So this is how you can consider this quantity. So here you take the what was it? Yeah, HP is here. So if you take 3 and 4 and fuse, you have a primary the conformal descendant primary field P, and P dependent P can be determined by just all the Virasoro generator acts on HP, and the contract with H1 and phi 1 and phi 2. And then up to normalization, you can determine this conformal. In particular, so this quantity can be just computed by just honestly solving this Virasoro algebra using computation relation. For instance, F0 is of course 1, F1. So this is a famous one. This was determined by BPC. And so on. I'm not going to write down. So this is a rational function. So rational function is some function which has the polynomial in numerator and the denominator. That's a rational function. Okay. And so one can ask the same thing to the yes, yes.
Why in this graph 1 and 2 looks symmetric, but in the formula we can't see the symmetry of 1.
I mean, so here essentially, I take the. I think I should write them the opposite way. Indeed, actually, I should. Yeah, here. Opposite. I should write down phi 1 0 acts on the cat bra and cat. I don't know which one bra is called. Is it bra and cat? I forgot. So phi 1 goes to 0, acts on here, and you get the H1. So it's just a position. Is it? I just put the 0 here, and the phi 2 is equal to 1. So therefore, which one acts on the vacuum? That's a problem. So that's why it looks asymmetric, but it's symmetric. So because here I already made some choice, infinity 1 x 0. So this choice will give you this expression that looks a bit asymmetric. Okay. And another way to do that, of course, one can consider, so one can another way to fuse is that you can just take another. So another way to fuse is essentially 4, 1, 3, 2, and is sum of Q, and then 4. I just got confused. It's a bit strange. I shouldn't use 4, 1, 3, 2, I think. Yeah, I think, sorry, 4, 2. So I think this is type of 4, 2, 3, 1. This is more better. So you can take the different way of fusing. So here you just fuse 3, 4, and 1, 2. But here you can take another way of fusing. So 1, 3, and 2, 4. And the intermediate channel you have a family of Q. So here I take. It's a bit strange. I think there are lots of typo here. Sorry, I need to fix it. So my notation is the. Okay, now I take. So here I think this is the case. Z2, Z3, Z4 is infinity, and then 1 minus x, and the x3 is the. So is x3 is 1, and the z4 is 0. Yeah. I think this is what I have taken. And you can have this expansion. And now, of course, you can have that different way of doing fusing. This does not affect physics. So essentially, correlation function of phi 1, z1, phi 2, z2, phi 3, z3, and phi 4, z4. So this is I'm actually a bit skeptical. So I'll fix my notation later in the lecture note and pretty precisely. Somehow lecture note looks a bit strange to me. So I will fix later. It can be written schematically C12P, C34P, and then this guy P 4, 3, 2, 1, or you can have this is P and this is Q, C 1, 3 Q, C 2, 4 Q, and this guy 3, 1, 4, 2. So this is the 4-point function. One can just consider. So it's a different basis. So this P is the primary you can fuse once you have fuse 3, 4, or here 1, 3. So in this way, one can have the equality between these two expansions, and then from then you can determine C by fixed level of descendant. Okay, so that's okay. In particular, so these two bases can be related by so-called fusion metrics. For instance, or fusion operating metrics. In particular, schematically, so people often write like this way. So 1, 2, 3, 4. Maybe I need to be careful about this. So this is B. 1, 3, 2, 4, and Q, and Q. So this is cooperative matrix. On the other hand, we have 1, 2, 3, 4, P, and then and Q. So there are different way of doing expansion. So therefore, so you can have they are related. So there are different bases you can consider, and then there is called fusion matrix. Okay, so that's what happened. And in particular, this minimum model and so on, in intermediate channel is finite. So in other words, if you take the phi 1 cross the fusion of phi 1 and phi 2, you have a finite many, only finite many whatever, Q1 plus phi Q2, or maybe P1. P1, P2, PL, finite many compound family you will get. Okay. You will get by fusion rule. By fusion rule, so you only so therefore intermediate channel so is only finite many. So therefore this matrix is just the finite size. Okay, it depends on P and Q. So finite size matrix. In particular, so this FPQ, another name is called Sixture symbol. So another way to go fusion matrix. Actually, if once you determine fusion and you have a so-called so they're actually related by some appropriate way of the unitary transformation. So once you determine fusion metric, one can determine Brownian metric, vice versa. A Sixture symbol. This one is the introduced by Wigner and in Polish. I think I should go to upstairs. And in quantum, like some people in here are interested in like quantum computing, so let me. So these are data to define a quantum computing and so on. I mean, most mathematicians, so CFT with let's see. Now, for instance, rational component filtering finite number, like a minimal model, primary, such as like minimal model. With it has, so we know it has S and T matrix. So S and T matrix acts on character. So in other words, you have a given a primary, you can determine the character, and this one is determined by sum of, it's diagonal matrix Q to the H, chi of I and T Q to the H I, essentially. And then chi of I minus 1 over tau is sum of Sij chi j of tau. Okay. So this is S matrix. Actually, T is too trivial. So S matrix and T matrix, and then so this fusion matrix and Brady matrix. Fusion matrix and Brady matrix, so-called Diesel form, so for modular tensor category. So based on this modular tensor, there are a modular tensor category. One can, it's a very important category. Anyway, yeah, it's a lots of relation, whatever TQFT, not invariance, and or quantum computing. It's called topological quantum computing, proposal Kitaev and so on. Kitaev, Friedman, whatever, Jem, these Microsoft people, and so on. Essentially, so here, what they call is that so if you have the 1, 2, 3, 4, and P, and you have a P is finite many. So if you have finite many primary, P is finite many, intermediate finite many. So this finite many object is they call qubit, and then you have a bunch of qubit. Whatever. I'm not familiar with the quantum computer, topological quantum computer, but essential idea is you assign one qubit into each primary cohort family, and then you have a whatever qubit, and you have a gate, and so on, whatever. This gate can be understood as a braiding. So for instance, you can just change it to like this way, and so on. So you have this operation, if you gate, can be encoded as a braiding acts on this qubit. So that's how you encode the information about this quantum computing in the modular tensor category. In particular, so this F and B satisfy so-called pentagon and hexagon equation. I'm not going to write down everything, but yeah. Okay. Let's see. So F and B will satisfy this following equation. Essentially, I'm not write down everything. B, it's same as Yang-Bak's equation. B. This can be understood as the 1, 2, 3, 4, 5 is mapped to 1, 3, 2, 4, 5, and then here 1, 3, 4, 2, 5, and then 1, oh my goodness, 4, 3, 2, 5, And then another way to reach there is take the another path. So here you just exchange 2 and 3 first, but the other way is you just do the 2, 4, 3, 1, 5, and then you have what I'm doing here. I forgot 4, 2, 3, 1, 5. And you just exchange 2 and 3, and you get this one. So you have to use B here, 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 you have to use B here. So essentially, the upper root is the same as lower root or whatever. Yeah. Up root is the same as down root. So therefore you get the Yang-Box equation. So this braided matrix should satisfy this Yang-Box equation. Sometimes it's called hexagon equation. I forgot. Is it called hexagon? I already forgot. And then also you have the same relation for fusion matrix. So you have you start with 1, 2, 3. Sorry, what I'm doing. 1, 2, 3, 4, 5, and then first you go to 1, 2, 3, 4, 5. And then just do the 1, 2, 3, 4, 5, and then you can just have 1, 5, 1, 2, 2, 3, 4. 2, 3, 4 is the same as you just first do the fusing of 2, 3, and 4, 1, 5. So you have to use fusion matrix, fusion matrix, fusion matrix, fusion matrix, and fusion matrix. And from here, what you get is FF is equal to sum of FFF. Okay, so this is called pentagon equation. This is pentagon equation. And this is called hexagon or Yang-Box equation. Hexagon or Yang-Box equation. Or sometimes it's called hexagon equation. So these are data to define the module tensor category, which plays a very important role in the topological quantum theory in 3 dimensions, and that's all. And topological quantum computing proposed by DIF and the Microsoft team. Any questions so far? Then I'll move on to renovation group 4. Yep.
What is primary means?
Huh?
A CFT with finite primary minimum model.
Yeah.
What is primary?
Primary field or primary operator. You know primary operator, right? Primary operator is T of Z, O of 0 is H O of 0, Z squared plus. So this is the primary operator. and you have finite many primary. So the CFT endowed with finite many primary operator. Minimum model is one of the examples. That's why it's important.
Why there is finite many? Is this has been improved?
I told you. If you specify, HPQ, HRS, but whatever HRS. But if this line hits into some point here, you have only finite many primaries in minimum model.
So primaries means the dot in this area.
In for instance, yes. Yeah. So that's why minimum model is exactly solvable. If you have an infinite many primary, it's hard, much harder.
Also, S matrix, STFB, this four matrix is the primary is the I don't know.
S and T and FB are determined by conformity theory, and of course, everything, all the conformal block, you need a data of primaries. And of course, as I mentioned, so internal channel here is only finite many. So that's why F and B are finite metrics. It's not infinite, like essentially n times n metrics. So intermediate, you have only finite many conformal family because there are only finite many primaries.
And what is the numbers on the vertex of this graph?
So this vertex graph corresponds to primary. So this is a 5-point function I mentioned. So if you consider phi 1, phi 2, phi 3, phi 5, so these are 5-point function or primaries. So everything is primary field. That is determined by conformal blocks like this way. And then, yeah. Any other question? Anyway, this part is not written in lecture notes. But anyway, it's written in many books. Any other questions?
And why you said the fusion rules, for instance, every M2 primary field can fusion into
What? Phi 1 times phi 2. But this is you already did a lot of your homework, right?
And what is the how can the right hand side illustrate in the graph?
So that's what I meant. So this phi 1, phi 2, and P can take P1 to PL. And you have, where did I erase? So here, sum of P means all possible conformal primaries, conformal family, all possible conformal family. So this P takes the body P1 to PL. So therefore, this is finite sum. So therefore, this did I erase F matrix? I think I erased F matrix, but this F matrix is finite size. In this case, L times L matrix. So any other questions? But in general, these are data on module tensor category. But determining F and B is usually very difficult. S is also difficult, but way easier than the F and B. But to determine F and B is very difficult. I mean, after we're gonna look, not so many program has been made. Not so many. So 1940, we don't have so much progress. Yeah. Yeah, so this fusion matrix is F is very difficult to determine, but yeah, my students, including here, made some progress for some was the middle with the model. So on how, and then my students made a small progress on this to determine F matrix, but not for big progress. No, I mean, some small progress instead has been made in my group. Okay. Okay, let's talk about the renormalization group flow. So renormalization RG flow, and then let's go. Okay, so that's what we're going to talk about. So we have so lattice. Let's start with lattice with the spacing A. Each side spacing A. Like this way. And the spin variable, we just consider sigma I1. Let's start with sigma I1. And now, okay. Okay, first of all, okay. And do the caustic grading. So I'm going to talk about the idea of renormalization group flow. And they do the cost grading, which means that I just do the average over the some region, whatever. I'm too lazy to write down everything. And let's consider the average over the following region. Say like this way. Maybe it's better to use other color, maybe blue. Like this way, and then so you just average all the spin to get that other lattice. Okay. So to do that, well, so the idea is average spin. Spin variable. And then obtain bigger lattice, obtain bigger, or like a coarse lattice, a bigger, or maybe coarse, bigger, or coarse lattice. Okay, so that's the idea to do that. Yeah. So you start with the Hamiltonian, which depends on spin variable 1 and the coupling constant G1. So this is coupling constant. And you do the cross grading. So you do the cross grading. So this is to do the cross grading. So we just do the average over sigma 2 of k is equal to some constant with the sum over I and bk k sigma I of 1. So bk is this one. Whatever. So this is bk. So this box is bk. bk. Whatever. K is a position of this box. K. Whatever. This is b1. This is b2, or whatever you call it. b1, b2, b3. B4, B5. K is just a position of the box. This is constant. A is some constant to average of some suitable normalization. And then now introduce the following. If sigma 1, sorry, I think I should call it this K and I. If sigma I of 1 is bk, I is 0. So if you introduce this one, so of course it's satisfied if you sum over all sigma k. Sigma pk and then 2, then this t sigma k of 2 sigma I of 1 is equal to 1. That's of course true. I mean, sigma I of 1 is some spin variable. Sigma 1 of I is some spin variable, and then sigma k is essentially you just move the boxes. So you sum over all boxes. So if box is here, if t is of course 0. So if you pick sigma 1 of I is this one, unless this yellow box or blue box, whatever you call it, blue box hits into the this region, you just get 0. That's what operation t does. Okay. So if you move these boxes for entire plane, at some point you hit this one, so you get 1. Otherwise you get 0. That's operation t does. So, and then we define the the new. So we want to determine H new Hamiltonian 2. So I call it H1. H2 sigma k of 2, whatever sigma, whatever we call it, HI, okay, and GK of 2. So I just want to obtain by coarse graining. So this is a coarse graining. How to say graining? So which means that you just average over all the spin variable to get the new Hamiltonian in terms of new spin variable sigma 2. To do that, we just have e to the minus h2 of sigma k of 2 gk of 2 so all blocks T okay, so you define new Hamiltonian or like a more like a Boltzmann weight by just multiplying all the, so you just sum over all possible states, but you just multiply these T blocks, okay? T blocks. So this is so previous Boltzmann factor, but they multiply T matrix which applied which connect the old spin variable and new spin variable. Okay, so therefore everything. So if you sum over all spin variable, you get the new Hamiltonian in new spin variable. So that's what it means. So therefore, new coupling constant can be written in terms of G, old spin variable G, by average over all the spin variable. That's the idea. So this T matrix will connect between all spin variable and new spin variable. So since due to this property, once you sum over sigma new spin variable, then if you sum over all the new spin variable, now sum of new spin variable. So what we did is essentially here, I think I should use this one. And then we just do this one. And since this, due to this property, if you sum over new spin variable, you get 1. From here, you get 1. Okay? So you just multiply 1. So therefore, this is equal to sum over sigma I 1 and e to the minus h1 sigma I 1 and gi 1. So therefore, the partition function agrees. So this can be understood up to kBT, Boltzmann constant temperature. This is Boltzmann weight. Okay. So therefore, the partition function agrees. Okay. After coarse grain. Okay. So in this way, so you can obtain by average over all spin, you get a new Hamiltonian. But that's called coarse graining, or it's called renormalization group. Renormalization group form. So therefore, so I don't need to write down everything. So new coupling constant G2K is some function of the old variable. Okay. some function. This is usually a very complicated function. Function. So likewise, so if you did so for G, okay, sigma 1 of G1 of H1, and by cross gradient you get the H2 sigma 2 G2, and you do the same thing, dot, 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 dot. And you can obtain the Hn sigma n Gn, okay, like this way. So therefore, coupling constant G will change as you keep doing a cross gradient. That's called the renormalization group trajectory. That's the idea of renormalization group renormalization flow. And one thing, physicists are very, and this is actually, I would say that it's a very bad habit of physics. I mean, they just try to coin the fancy name and so on, and then, which is not appropriate. First of all, so one caution is that the renormalization group flow is not group. So renormalization group is not good name. So which means because it is not a group. Not a group. Okay. So first caution. So as you know, so this is cross gradient. Okay, you can determine from H1 to H2, but you cannot go back. Okay. So if you have in the group, if you group G, element A, there must be A inverse in the, okay. This operation, if you call this operation is A, there must be operation A inverse. Okay, but this is not the case. So therefore, it's not group. Okay, so therefore, the physicists mistakenly give the coin the name. So it's better to go. I mean, RG flow. It's better to put that flow, definitely. Okay. So I would like to use RG flow instead of renormalization group. So that's why I use the RG flow over there. Another thing is often in quantum field theory, I don't know, I mean, I don't think shouting you reach to the renormalization group, but eventually you will learn this how you evaluate the one loop correction to the electric coupling constant E, electric charge. So that's the one how to say instance to learn renormalization group flow, RG flow, but to compute this one loop diagram, you often do the regularization to get rid of infinity. But unfortunately, so this renormalization group is not the RG flow, or a renormalization group flow is not a technique to remove infinity. So of course, when you do the calculation, one has to set some like a UV cutoff and then just get rid of like add the counter term, and then to get the final answer. And that's how you compute one loop diagram, or how you obtain the one loop quantum correction to this electric charge, but unfortunately, as I mentioned, so it's just a coarse grain. RG flow is just coarse grain. If you start with very like a tiny you just start with A. This distance is very small. Okay, so people just said that 1/A is equal to lambda. So this is UV cutoff. You introduce, and then get rid of the how to say to get rid of the dependence of lambda. So that's how you do that. So you just start with a very small how to say length and do the coarse graining. That's why lambda is very big. So that's why you encounter the infinity. But unfortunately, so the renovation group law is not the technique to get rid of infinity. Just you start with the theory define a very, very high energy scale and do the average over, and how the theory will change. So that's the idea of this idea is given by Wilson. So this is called Wilsonian. Sometimes it's called Wilsonian renovation. That's a two question I have to make. Okay, let's look at the example of this idea. This idea. So be careful. So be careful of these two issues. So you will learn shouting use class. I think yeah, most likely QFT1. You just consider the one loop correction electric charge and do the one loop correction and do the lots of technique of Feynman introduce Feynman parameter, get rid of whatever, and introduce counter term and so on, and obtain obtain the result of this Feynman Schwinger Tomonaga. That's I think one of the main goal of QFT1. But just keep in mind once you when you learn renormalization group, whatever, quantum correction.
So, renormalization group can be taken as semi-group.
Semi-group, maybe. I don't know the definition of semi-group. I don't know. Okay. And eventually, yeah, I don't know, he would teach QFT2 or gauge field theory. But eventually you also learn the same thing for quantum Yang-Mills. And you see asymptotical freedom and so on. So anyway. Oh yeah. So then you start with the whatever, and the coupling constant G1, G2. So suppose there's a two coupling constant in theory, you start with whatever. This point, G1. And do that this renormalization group scheme, you just move to G2 here. Okay? And so on. And after the G3 and G4 and so on. This is called really flow. This is called really flow. You just change the coupling constant as you do the coarse graining. And at some point, even if you do the coarse graining, it doesn't change. The coupling constant does not change. That's called fixed point. So which means that the G star, did I erase? Oh yeah. So here, G star of n plus 1 is equal to G so at some point you encounter such a situation. Even if you put the same value of the coupling constant renormalization, this is called fixed point. So often it's called Wilson-Fisher. Wilson-Fisher. fixed point. Or sometimes called IR, infrared. Let me write down infrared fixed point. Or IR fixed point. So therefore, even if you use the coarse grading, the coupling constant does not change. So therefore, Hamiltonian does not change. So therefore, the theory is independent of scaling transformation. Essentially, coarse grading is a scaling transformation. Even if you zoom in or zoom out, the theory wouldn't change. So therefore, the theory is scaling invariant, and then the theory is very like a well-defined physical theory. There's an argument. There are lots of arguments. If the theory is not like a pathological, so scaling invariant somehow means the conformal invariant. Conformal invariance. If physical theory is a good theory. It's a very well behaved, a good theory. It's not pathological. Good. So there are lots of arguments. I mean, scaling transformation is very like a very small small part of conformal invariance. Conformal invariance is much bigger than infinite many generator, as you know, in 2 dimensions. Okay. So the scaling transformation is one of the conformal transformation that you already know. But somehow, in physics, theory is scaling invariant, which means the conformal invariant. But there's no proof, indeed. But unless you start with very strange theory, this is true. So therefore, the people believe often that the at IR fixed point, even though it's a scaling invariant, means the conformal invariant. So therefore, the IR fixed point, the theory is conformal field theory. Okay. Let's take a look at the example. So one-dimensional Ising model. Okay, so Ising model. And then again, Hamiltonian, let's see. Hamiltonian is given by, as you know, SI, S. Oh, by the way, Shu-chan, thanks for the lecture notes. He helps me a lot on writing on the new part. I, so this is I, or whatever. And do the coarse grading, and then we know Boltzmann weight. So Boltzmann weight is given by e to the j s I plus 1, and then we know this can be written cos j plus 1 plus times j times si and si plus 1. So you remember, right? So you remember this is true. Okay. I hope everybody understands this. Okay, so then do the average over. So the average over is you just start with the okay, let's do this example. So let's consider 3 block. Let's go S1, S2, S3, S4, S5, S6. And then we call. So you just average over, seriously. And let's call it this one. This guy is the sigma 1 and sigma 2. And you average over in the middle. Okay. And do the same thing for next level for 2, like this one and this one. Okay, so we just do the following average over S3, S4, J sigma 1, S3 plus sigma 3, sigma S4 plus S4, sigma 2, so on. Okay, so this is what you do. So you just average over 3 and 4 and keeping fixing sigma 1 and sigma 2. And this one, just plug this one into here over there. This can be written as root cosh j cube sum over 1 plus times j sigma 1 S3 1 plus times j sigma 3 sigma 4 1 plus times j sigma 4 sigma 2 and then S3 and S4. Okay, this is a very easy operation one can do. And then this is cos j cube 2 to the cube and then 1 plus times cube sigma 1 sigma 2. I mean, you just insert, just do the honest calculation. Insert sigma 3 is plus 1 and then sigma 4, essentially you have only 4 possibilities. 4 summation. So and then obtain this one. So you can just do the honest calculation. You can obtain this. Okay, so this means that what matters is the one part. Okay, one part, and you just multiply these two parts. And in the cross term is if you average over, it will disappear. Do you understand? Cross term is for instance times j and 1 times this one and so on. You have only times j squared, right? But if you do the sum over there, they'll all disappear. Only what matters is this guy and this guy. Okay. So therefore, you get the similar form as before. So this Boltzmann weight, if you average over, if you compare between them, so tanh j is replaced by tanh j squared and the tanh j cube. Sorry, I missed tanh j cube, and the prefactor is changed to the like this one. Okay, that's the only change you will get if you do the average over. So therefore, so one can consider the times. So here you can treat it as, this can be treated as tanh j tilde. J tilde is a new interaction constant. So J is a coupling constant. Okay, J is coupling constant theory. That measure how they interact with the. So that's that measure the interaction between adjacent spins. And if you do coarse graining, the value of J will change to J tilde. They are related by this relation. So therefore, if you write down the new Hamiltonian with the spin variable, new spin variable, J tilde, and you can just write down some constant. And tilde and some function, some constant shift, and then new tilde. What's important this time? J tilde, sigma I plus 1, I belongs to something. So n tilde is a number of sides, which is of course we just do the 3 spin into the 1 spin, 3 spin to 1 spin. You just average over 3 to 1. So therefore the total side is n over 3, and the shift is given by this function. But the shift is not so important. I mean, just overall shift of the Hamiltonian, and this can be understood as minus log. I mean, cos JQ minus 2 log 2. So this is how we obtain. And J tilde is, of course, from here you can just obtain by J tilde is equal to tanh inverse and tanh JQ. So that's how we obtain relation between new coupling constant, old coupling constant, and new coupling constant. So that's the one example of the renormalization group equation. Okay. And where's the fixed point? Fixed point is the, of course, so tanh J tilde is equal to tanh JQ. Okay. Tanh J tilde is tanh JQ. So therefore, this fixed point is either J is equal to 0 or infinity. 0 or infinity means that the so 0 means really high temperature. Yeah, 0 means very high temperature, and infinity means the zero temperature. So this is a high temperature, and then 0 temperature, it becomes fixed point. So that's one-dimensional Eisen model. Okay, let's take a break, and we'll talk about the beta function Colin-Simons equation after break. Yeah. Let's take a break. If you have a question, just let me know. Did you find something?
I didn't really understand why these two operators correspond to.
So this can be obtained by
大家把那个助教的考核表提一下，然后填，不用刷了，随便填。
I mean, consistency of the this kind of stuff. But if you take the sigma mu, you should get the psi, and so on.
Phi. And what's the relation between phi and sigma mu?
Phi. So sigma can be obtained by phi 1 2, phi 2, 1 2, but mu is acting on 0, acting on sigma. So V0 is the some generate of some mode, fermion mode. Then you can get everything. So if you identify like the operator in the Eisen model with the primary of the minimum model, then everything becomes consistent. That's how they find and how you obtain identify the minimum model with the Eisen model.
This all times. This is a.
It's tensor product. Well, yeah, it's tensor product. So you have a holomorphic primary and anti-holomorphic primary, and you just need to take a tensor product.
This is the tensor product.
Yeah, actually this is not tilde, actually bar. Yeah. And the 511 is identity operator. Identity or vacuum. Oh, I see. Oh my goodness. It's cool. Yeah, I mean, you're right. I mean, what you said is correct. Yeah, I just want to. So the first one, I just want to give some idea, but the concrete calculation this is enough. In other words, what I did is that yeah, I mean.
Maybe I can really wonder from the physical point of view, it's going to be the closed screen. I can't see single screen, right? I only see
I understand what you mean. So, I mean, you can do the essentially average over these three sides, and you can call it sigma. You can call it that's the first part of the lecture. That's the method I told you. But practically, you can do just the sum over the no, I just do this practical calculation. I mean, if you try to do this with sigma, try to define sigma as all sum of all three spin states, the calculation becomes more complicated. So, but here, so I just did a much simpler computation to average over. So what I mentioned is a bit different from what I'm doing here. But essentially, what you're doing is the averaging over. So I mean, you will get the same result even if you do the same.
So what you mean is this definition is not for practical calculation.
Yeah. This definition is not practical calculation. So I just do the simpler calculation here.
Okay.
Yeah.
Okay, maybe I should learn more too.
Okay. Yeah, I mean this one is just idea. Try to give you idea. The previous one is to try to give you idea, but practical calculation you can just sum over these to get the course grain.
Thank you. 这是我们从正常的就是当的。那它4个点的
对啊，就是这个问题。
可能我的说和这个每天，我本来口来一句。那给我来一个缓慢释放。哎，你的那个物理的问题免费。物理所也可以免费。但是他们博后可以。然后他们就用博后的。
I think this process is just take 2 of them as the work.
Yeah.
我有一个很多人在考虑。一个他一个月就不到他。今天还一天啊！我靠！现在
Yeah. So what I explained is that in the previous one I have to sum average of 3 spin to make it sigma. But here we just average over 2 blocks to the practical calculation. That's what I tried to.
我那边是属于我上次跟那边讨论，所以我什么都不需要做。我也特别喜欢养绳子不大好啊。
我也有绳子。
那你说
这里就是说，因为这个新的挖有的是上指对对方的这个发展的上指为啥？那你这个地方呢？我这个看到我你也魔怔，我也魔怔。你继续做一个赛事。
能把影响清楚的是希望我还是希望这个不能拿来就是他没有 S。
啊，就是给了一个 framework， 但是算不出 details， 但什么都算不出。如果太难了，如果它的数学力也是属于，就是真正就是数学那难物理，所以就是就是说以后他前面1老师都是正常嘛，对吧？如果你直接把对，我是说你想知道你的，它有非就是非常长的，你先说好的那个东西 ，average， 它是不能 exact， 如果写3个平均，我写过这个东西，我想说如果3个都是实在是做
Okay, shall we resume? Let's see whether I can reach to the Ciscarian. So now we talk about the charismatic equation, the beta function. So it's a very So you start with some theory, conformal field theory, S with the action star, okay, and perturb. Perturb. So which means action. So this action S perturb series star plus A, and you just add interaction term. So this is the some operator, whatever operator it is, okay, and G is the coupling constant. Okay, so that's how you perturb. So without this perturbation, the theory is conformal. But now you perturb it, so it's no longer conformal field theory in general. And then we take the GA is sufficient small. That's why it's called perturbation. Okay, and then it has a scaling dimension, so consider scaling dimension. Dimension is sigma A. Scaling dimension has a sigma A. Okay. So therefore, to make the theory consistent, it has a scaling dimension of -2. So it has a scaling dimension -2. So therefore, GA has to be scaling dimension should be 2 minus sigma A. Okay, in order for the whole action to be the dimensionless. Okay, whole action to be dimensionless, it has to be the scaling dimension coupling constant 2 minus that like. Okay. So another scaling transformation, x goes to x times 1 plus d lambda. I don't know why I call it d lambda. Okay, I think it makes sense maybe. Okay, so let's follow lecture note again. Under the scaling transformation, so then this S is transformed as star plus sum over A 1 plus d lambda. Like this way, and then we assume d lambda is very small. Assume d lambda is very small, so that then delta s can be understood as d lambda 2 minus delta a d squared x ga. Like this. So of course a star is scanning invariant, or more precisely conformal invariant. So on the other hand, we know that the theory S under scaling transformation delta S is whatever, I don't know the normalization, is delta lambda d squared 4. We already learned that this is the case T mu mu. So in the first, second lecture, third lecture, I already explained this one. More precisely, do you recall this one? I hope that, as far as I remember, under any transformation x mu goes to, delta x mu is epsilon mu of x, and then delta s is something like d squared x t mu nu. I don't remember mu a, like this one, right? As far as I remember, some number. I don't remember a number. And then so scaling transformation is just a scaling transformation. This is x mu d lambda. So d lambda, plug that one into here. Essentially, you get here d lambda, delta mu nu d lambda, and you get this one. So I think I should call it this trace part, right? Yeah. So I should write down like this. Sorry. I think in my lecture note, I think I assume the Euclidean signature and then matrix delta mu. Okay. So this is the under the scaling transformation, action is transformed. So that should be the same. And defining the setter, big setter is equal to 2 pi d mu mu. Set over x can be written as 2 pi. Yeah, I mean, as you already noticed, as we move to at the end of lecture, I make a lot of mistakes, so be careful. Like this way, so you can just trace part of the surface energy density can be written like this way, and then more precisely, where the beta A of G can be understood 2 minus delta A GA. Okay, so I just okay. So the beta function here actually measures. So measures how the coupling constant change under scaling transformation like this. So here we just perturb the action and then look at how it behaves like under scaling transformation. And under scaling transformation, under the scaling transformation, you get this kind of behavior. So therefore, the beta function here is indeed actually depends on this 2 minus delta A. And of course, in the fixed point, or fixed point or conformal field theory, so this beta function has to be 0. So as you recall, in the conformal field theory, this trace part is 0. Trace conformal conformal field theory, trace of stress energy intensity is 0. So therefore, of course, beta function has to be 0. Okay. So therefore, at the fixed point, beta function of G has to be 0. Of course. And if we start with conformal field theory and you do a small perturbation, so therefore, this equation would tell us. This equation tells us that the coupling constant grows like this way. Around the fixed point, GA should depend So therefore, if so if delta A is less than 2, the coupling constant GA increases as you scale up. If you go to infrared, lambda. As you increase lambda means that you just go to infrared, okay? Coarse graining. So then the GA increases, okay? So you can easily see. On the other hand, so therefore it's correlevant. Therefore it's correlevant. Relevant coupling constant. Relevant means that it becomes relevant in the infrared. So if you increase the scale, the coupling constant becomes bigger. So it becomes relevant in IR. So on the other hand, sorry, so delta A equal 2 decrease. So therefore this is called irrelevant. So irrelevant coupling. So it becomes irrelevant at the infrared. So delta A is equal to 2 is called marginal. So we don't know actually. So this is, we just consider only small perturbation. It's a classical analysis. Classical analysis means we just only care about scaling dimension. So therefore, it's a really classical analysis. But there are lots of quantum correction you need to take into account indeed. So therefore, we don't know what's going to happen indeed. So this is called marginal coupling. So marginal, we don't know. So I mean, classical, it just become a state constant. But it depends on quantum correction. It can decrease or it can increase. Okay? So that is indeed depends on this beta function. When beta function, so let's talk about this case when beta function A is greater than 0, it's called the marginally relevant. Because as I mentioned, so beta function I define like this way. So G depends on lambda is the positive, then the coupling constant grows. Coupling constant grows as you go to infrared. So this is called marginally relevant. Marginal relevant. And this is, in the case of this one, it's called marginally irrelevant. Okay. And of course, when beta equals to 0, so beta equal to 0 means exactly marginal. So if it is the theory is has exactly marginal deformations, which means that you can, even if you add this perturbation, sorry, maybe I should write the Lagrangian star. So Lagrangian star is a CFT, but even if you add exactly marginal operators, the series stay. Sorry, not beta GA, sorry. The series stays conformal. So it's called exactly marginal deformation. On the other hand, if you add a marginal relevant or the relevant operator, theory is indeed the theory is indeed actually flows to somewhere else, most likely. Flows to the other CFT. So it's no longer CFT. So schematically, so in the lecture note, in the first lecture, I just briefly explained the serial coupling constant. The serial coupling constant, or like the space of series. So it's parameters with lots of coupling constant. And you have a compound fixed point, but if you the compound fixed point, so this is CFT. If you perturb the theory by irrelevant deformation is so even if you perturb irrelevant direction a little bit, but then the theory move back to CFT because if you scale up or if you go to the IR, the coupling constant decreases. Even if you perturb like this way, GA goes to 0. GA goes to 0 as you move to IR. Okay, so therefore, so the irrelevant deformation is always moved towards the CFT. Even if you perturb, you move back once you go to IR. Okay? On the other hand, the relevant deformation is the opposite. You go to somewhere else from CFT. So this is relevant deformation. So it's a relevant deformation, which means that if you perturb the relevant operator, then the coupling constant grows. Coupling constant grows, and it goes to some other CFT, most likely. That's also true for marginally irrelevant, marginally irrelevant. If you deform the marginally irrelevant due to quantum correction, classically you cannot measure due to quantum correction, so it moves back to CFT. But if you perturbed by marginally relevant deformation, you go to somewhere else. How about exactly marginal? Exactly marginal now means that there is some other direction. I mean, let's consider 3 dimensions like this way. So this orange hides all CFT. These orange are all CFT. CFTs. Different CFTs. Even if you perturb by exactly marginal deformation, the series stays the same. So series stays CFT. But the series is different from the original one. So therefore, there is a, how to say? The space of CFTs. There is a space of CFT parameterized by exactly marginal deformation. So that's the, yeah.
By the way, I think the definition of synapse should be 1 over 2 pi.
What?
I mean, in the lecture nowadays, the coefficient of this 2 pi.
Strange?
Yeah.
Okay. Okay. So coefficient may be strange, but yeah, you're right. I think. Anyway, so I think. So this is 2 pi I. So there's a 1 over 2 pi. Yeah. Hey. Okay, so that's the case. And then, so universality in quantum field theory is that even if you start with some some other theory, whatever. So I mentioned in the first lecture that quantum theory has some universality. For instance, Ising model, even if you change the shape of lattice, and even if you a little bit change the interaction, the theory flows to the same quantum field theory. But it's the same thing. So here, this point and this point, the quantum fields are very different. But if you go to IR, everything flows to the same CFT. So therefore, so if you stay in this how to say irrelevant deformation, everything flows to the same CFT. So that's called universality. And this phenomenon is in any dimension. So let's talk about the semantic equation, of which talk about how it behaves, the correlation function, and so on the algebraic flow. Let's talk about the common semantic equation, which is the in correlation function in quantum field theory. So this is actually indeed for general. Quantum field theory, one can consider the correlation function of quantum field theory is just defined by the final path integral y1 of x1 xn e to the minus s of 1. So this is Euclidean thing which I use. And then on the Ciscarian transformation, we know that the delta phi I of x is defined as the, so this is we already know, x mu plus Ciscarian dimension with phi I of x. That's what you obtain. From the analysis of the symmetry analysis. So then Takahashi identity will tell us about the so this the correlation function is okay, so there's a typo in my lecture note. So this is xi mu correlation x mu I mu plus delta I hat acts on phi 1 dot phi n correlation function I runs from 1 to n minus, and then so since the current of Ciscarian transformation trace of I think I already erased here. Current is the trace of the stress energy tensor, and this is Takahashi identity. Okay, so this is Takahashi identity. Okay, so this is Takahashi identity. Okay, so since the okay, then I got confused by something. So let's consider the following. The correlation function, of course, depends on the correlation function. S depends on coupling constant, And correlation, so therefore correlation function depends on the depends on the coupling constant, and we want to measure how it behaves under the let's see. Under the change of coupling constant and correlation function. So let's record the how did I go? How did it go? I already forgot how did it go? How it goes? Sorry, let me think. Okay, so, yeah, so if you rewrite the sum of beta A, GA, so this is indeed given by beta A. This is oh goodness, phi 1 to the phi n. So this is what we want to measure is how this correlation function depends on the decoupling constant. And this can be understood as the G acts on sum of I, 1n, and beta A, sum of beta A acts on how it acts on GA, and then acts on this essential field. Sorry, so essentially field acts on GA, maybe phi 1. Phi I, partial GA, total phi n. So that's acts on phi I, acts on. And then, of course, it acts on the action. It acts on action, which will give you the trace part. Theta I, phi 1. So this is so first of all, so GA can act on the, okay. So the correlation function. So this is A. So the correlation function is defined by inserting this operator and times this usual time path integral, and GA can act on the operator. Also, GA can act on the action S. And beta A times derivative of GA will give you this the trace part. Trace of stress energy tensor. So therefore, so essentially the dependence of correlation function on the coupling constant is measured by how the coupling constant so the phi field depends on the GA and also trace of the stress energy tensor. So this is the how you can measure the dependence on coupling constant, and then if you write the how the derivative of GA acts on the operator like this way. So if you write this partial GA acts on the operator phi I on X, maybe did I write the phi I? Okay, good. Phi I acts on, I mean just schematically write down like this way. So this is just notation of phi I. Then this equation, combining this Ward-Takahashi and then this guy, and then what you get is the following operation, following equation I is equal to 1, and then x mu I partial x mu I and plus gamma cut I and G, and then phi 1 of x1 dot phi phi n xn. Okay, and minus sum of beta a g function ga phi 1 of x1 phi n xn. Okay, so where the delta hat of I can be understood, you just combine this delta I and this guy. This guy can be written as the P1A hat. Okay? P1A hat. So you just combine them. So delta I hat plus sum of beta A and beta I. Any question so far? So you can obtain this one. So you just combine one Takahashi entity and so the just definition of the how it behaves, the correlation function under the change of coupling constant, you can get this equation. So this is called Kalan-Simons equation. Okay. Yes.
The that formula is the definition of how to derive it.
So this the equation. Let's see how to derive it. So how to derive it? So let's see how to derive it. So here, so you just ask this guy into the. So this one is you just ask this guy into the each operator here, and this theta of why I call it theta y? Oh, sorry. So this guy, how you obtain is that you take. Oh yeah, I think what I did is that I see. So essentially, delta S delta GA is equal to operator A of X. Do you agree? Do you agree? So S is equal to S star plus some D2X GA operator A sum over. So this is a S, what we have. And if you take the variation GA, you get the operator A, right? And multiply beta A, and yeah. So the essentially up to constant. I think I may make a mistake. Sorry. D square X operator X. Okay. So this is the case. Yeah. And that's why maybe I should go Y. Okay. And I multiply beta A. Or beta A. And sum over A, and this is indeed equal to 1/2 pi theta y. Theta y, yeah. Okay. And that's how you obtain. Yeah. So that's how you obtain the theta y, and the combining these two equations, you get the Kalan-Simons. Two equations. Or Takahashi, in this formula you get the Kalan-Simons equation. Okay, 30 minutes has been left. So stress and energy tensor is what is the stress energy scaling dimension stress energy tensor? What is the scaling dimension stress energy tensor? Yeah, 2. So, okay, energy moment tensor, stress energy tensor same. I have a habit to call, I have a habit to call it stress energy, but lecture notes is it's a 2. Okay, so therefore the gamma acts on theta. Trace part of the stress energy tensor is indeed 2 theta. Actually, it's the stress energy. The tensor with respect to variation of GA is 0 because of the energy moment tensor is conserved under the independent of the coupling constant. So therefore, you can obtain the gamma hat is 2 theta. Acts on theta is 2 theta. So you can ignore this part, and they plug that into here, and then what you get is that the so gamma. From here, one can derive that the gamma hat of operator x is indeed equal to gamma b, gamma ba operator b of x, where the so this is equal to b to delta ab minus partial beta b of partial ga acts on operator on b of x. I really got confused what I'm doing here. Why is that? Sorry, I just got confused here. Gamma acts on A, operator A is sorry. I already lost what I'm doing, to be honest. What I'm doing here? Yeah. Sorry. So, sorry, I just got confused. But if you assume beta A, beta B is equal to e to the 2 minus delta B lambda or GA. Oh yeah, GA. Lambda. Sorry, I think, did I make some mistake here? Sorry, I got confused. I think something wrong here. Okay, I think let's keep it later. It's better to move on to, I think it's not, okay, this part I just got confused. This part, let's talk later. So, you use this column semantic equation. Does anybody understand what I have written here? Of course not, right? Also doesn't understand. So use column semantic equation, one can derive the Damascus theorem. It's better to move on Damascus theorem. Okay, so this part I will explain next time, and then let's move on to Damascus theorem. Okay. Okay, so C theorem, so this is a remarkable theorem, and it's a, so if you assume the rotational invariance, and also unitarity, and then energy momentum conservation. In two dimension, then they exist. Quantity C depends on R. Depends on scale R or lambda. Let's call lambda, maybe. Lambda, I call it lambda. Did I call it lambda? Okay, there exists function lambda and such that it's decreasing, non-increasing, yeah, non-increasing. Non-increasing function, non-increasing along as lambda goes to whatever, as lambda grows. So this is the numerical C theorem. And moreover, at a fixed point, and also n C at the lambda goes to infinity, which is a fixed point, is central charge. Central charge of IR fixed point, RR CFT. So this is the thermal C theorem. So if you assume rotational invariance series, two-dimensional series, a rotational invariance, and it's unitary and energy momentum conservation, and then there exists some function C which depends on the scale lambda, such that it's non-increasing or more precisely precisely speaking non-increasing, or most cases it just decreases as lambda grows, and then when you go to IR fixed point, it coincides with the central charge C of the CFT. So that's the theorem of the Zamonchkov, and we will prove by using this the Kalan-Szymanski equation. Okay, so we know that the energy momentum conservation. Energy momentum conservation variation is T mu and mu equal to 0. Okay, and then T mu nu is symmetric. T mu nu is symmetric. However, in general two-dimensional field theory, it's no longer decreased. It's no longer traceless. In CFT, it has to be traceless. Okay, CFT. But in general 2D theory, T mu is not 0. Okay, this is not true. So it's not traceless. So therefore, we just write down this energy momentum tensor in the 2D language in complex plane. So this is P plus 1/4. Okay. So as you recall, so I call theta is equal to T11 plus T22, and the theta T is holomorphic part is how did I define? T1 2 plus I T22. Oh, how did I define T? I already forgot. TZZ, essentially TZZ. So which means what? I plus so TZZ is T11, T22, and T12. So it's a linear combination T11, T22, T12 up to some I think something like this way, plus minus. I already forgot. It's written in lecture note. Like this way. So just write down this stress conservation of energy momentum tensor in terms of holomorphic language you can obtain like this way. Okay. So at the fixed point, so the CFT this Sailor has this. Okay. CFT, but on the other hand, yeah, on the other hand, you can have the. On the other hand, so the general series set is non-zero, and since so we take the so the T and the T bar, T Sailor and T bar in the for spin is of course 2, 0, minus 2 because I mean as a holomorphic line it's ZZ component 0 and this trace components has to be 0 and T bar has to be minus 2. So therefore, if you consider the following under rotation of the two dimension, so therefore dimensional analysis and also this rotational invariance will tell us that the T of Z, Z bar, and T of 0 and 0 has to be equal to Z to the fourth. It's holomorphic quantity F Z Z bar. There's some so since this is the how to say the scaling dimension is equal to 2, so therefore you have a 1 over Z to the fourth, and also if you have this guy T00, so which is the same as T Z Z bar and Sailor 0, 0, and then we have some function which determined by the length, which is determined by length, so Z Z bar. Length of a theory, and then you have a Z to the cube and Z bar. So you have, so theta depends on one over Z and Z bar, and also here you have theta Z and Z bar, and then theta 0, 0, and then this one is equal to h some length Z T bar divided by Z squared and Z bar. So this is coming from these rotational invariance and also these spin and the dimensions of the operator. So T should be depends on holomorphically, and it should be coming from 1 over Z squared because of the scaling dimension. So it's a scaling dimension has to be 2. On the other hand, scaling dimension of theta has to be 1, 1. Okay, the holomorphic. So TZZ, and essentially theta is T Z bar Z bar. Okay, essentially theta is Z bar component. So therefore, the essential scaling dimension is 1, 1, and this is 2, 0. This guy scaling dimension, holomorphic and anti-holomorphic. Therefore, this denominator power should be come from the scaling dimension of the T operator. And then, since we assume the dependence coming from of the correlation function is, rotational invariant, it should only depends on the radius of the numerator should depends on radius of the series. Okay, and then combining so this equation for energy momentum tensor conservation. So then what you obtain is that you can have the following equation. So if you plug this conservation energy momentum tensor and compose with T, you can obtain this one. You can obtain this one, and just what we are going to do is just plug this one into here and see what's going to happen. So to do that, so we just define F dot as the ZT bar, and then F prime of ZT bar. ZT bar is only ZT bar is of course equal to Z squared, right? Z squared. It's just a radius of the position, radius square of position, and you just take a derivative with respect to radius essentially. Here it's just a derivative with respect to radius up to some correction. So and plug this one into, so this is the exercise you have to do. So this is a homework in this week. So plug this one into here. What you obtain is that the F dot plus 1/4 G dot minus 3/4 G equal to Z. So plug this quantity into here, you can obtain this one. So this is the exercise you have to do. And we have to do the same thing for combining Seder. So we just need to do the same thing of Seder. So partial bar of D and CZ bar and Seder of 0 plus quarter partial Seder Z bar Seder and 0. So that's what you do, and plug this one into here, and you obtain. So this is also exercise to do. The derivation of this one is next week's homework. You guys doing still homework this week?
The definition of G dot is the same as F.
Yeah. So this is essentially any function. Any function. Yeah. And then you just get rid of so you just get rid of G. You just get rid of G. So and define a function. So let's get rid of G. So let's multiply minus 3/4 and just add them up. So then what you get is indeed. I hope I'm not going to make a mistake. So minus 1/2 G dot. And then you have this guy. So minus 3/16 H dot and plus 3 of 8 H equal to 0. Okay, so that's what you get. Do you agree? Or I might make a mistake. Yeah, I think I'm correct. And then we define the following quantity: C is equal to 2F minus G minus 3/8 H. Okay, so essentially 2 times this guy. 2 times this guy. Forget about dot upstairs. So you just 2 times this guy, and from here, what you get is 2 times C dot plus 3/8 H is equal to 0. Okay. Okay. So we know, so therefore, so this C dot, I might make a mistake. Oh, whatever, you guys should correct me. So 1/2 C dot. Okay. 1/2 C dot is, so this one half of the two issues we just want to have some function which coincide the central charge C. So therefore you have to properly normalize. So that's the proper normalization. So then C dot is equal to minus 3/4h. Okay, so this is the case. And we know by unitarity, these two correlation functions should give you some positive answer. Okay, so therefore h has to be positive always. So by unitarity, positivity. So therefore, this should be decreasing. So dot is essentially, you just consider the rotational invariance. So it only depends on the position, radius of position. So therefore, C dot is decreasing consequently. Okay. Oh my goodness, I shouldn't erase this. And now, so we will use the Collins-Simons equation. So Collins-Simons equation 6.11. Sorry, I think I make around here some note is a bit strange. Okay, I will correct later. Sorry, I shouldn't erase central charge. Central charge of, so this is statement. So Collins-Simons equation, so R, so partial R is sum of beta A G. And indeed, this is indeed, if you use Collins-Simons equation, you can just C of R, dependence R. R is equal to Z, which is current DC bar. Now, it depends on coupling constant G equals 0. So this derivation, I haven't written very carefully. So C function appear here is defined like this way. Okay, let's for timing accept it. So this is the constitutional Collins-Simons equation. Collins-Simons equation. I will explain that next time more carefully. Collins-Simons equation. The equation. Then what you can have is that we can obtain. So using 6.5 is so just recall the Sator of x is equal to 2 pi sum of a beta a, and then operator a of x. So using this one, then the renormalization group equation one can obtain from here. So you can have beta a partial g a is equal to CG. CG acts on minus 3 half GAB G beta A of G and beta B of G. Let's see. So where the G of AB of C bar G is equal to sum of product of operator C bar and operator B. So this metric is given by this correlation function of the operator, which is positive definite, which is not positive definite. Definite because of the unitarity, which is positive definite. So this part I will explain a bit more carefully next time. So I just give tell you the consequence of this equation. So using this one, so GAB, so this GAB is positive definite, and so it's called Zamochkov metric. And since it's positive definite, you can have an inverse matrix. So therefore, beta A. So I don't have time to. So next time I would spend a bit more detail. Minus 2/3 and sum of B. You have an inverse matrix GAB inverse partial C partial GA. Okay, partial C. So the beta function of the operator can be obtained by the derivative with respect to the C function. And then since the fixed point C is indeed F, I already listed the fixed point at the fixed point. F is equal to C over 2, and G is equal to 0, and H is equal to 0. So therefore, if you plug the definition of C here, you can easily see that at the fixed point, C function of R goes to infinity. This is equal to the central charge. So this is by definition over there. So the F is obtained by TT correlation function, whereas these guys involve the Sator, coming from Sator. So therefore, it should vanish at the fixed point. On the other hand, TTOP, you get the C over 2, so therefore central charge has to be, you should obtain the central charge. And since, at the fixed point, sorry, so I don't have time. So since this is a decreasing function, you always have CUV is equal to CIR. CUV is CIR, and this always like this way. So therefore, C can be understood as it measures some degrees of freedom theory. So that the if you go to the IR, you have to average over. So therefore, many information degrees of freedom we average over. These are decreasing IR. So it can be understood as it measures the degrees of freedom of the theory. And at the IR fixed point, so therefore central charge can be understood as the degrees of freedom at the IR fixed point. Okay, so this derivation is a bit rough, so next time I will explain a bit more detail. Unfortunately, I didn't do a great job on the renormalization group flow part. I will explain this part on the later, but you understand the idea. You just start with the correlation function, stress energy tensor, and then use the Curran-Smuts equation, you can obtain the decreasing function. Okay, so let's stop here.